two final model or modeling examples that we're going to consider is the pendulum oscillator as well as fluid systems. Let's look at them now. So the contents of this lecture, we'll look at first the pendulum model, consider the Newton's laws of motion and how it applies in case of the pendulum model. We'll look at modeling itself as far as the pendulum model, and we'll talk about linearization of a nonlinear pendulum model, because naturally the pendulum model comes out as a nonlinear system. And then for fluid flow systems, we will consider as a preliminary Bernoulli's law, and then we will subsequently then also consider conservation of mass and how it can apply to fluid flow. And afterwards, we will look at an example of a level control for a fluid, and then we'll also consider then linearization, because the model that is going to come up out of the example will be nonlinear. So now the pendulum, it's a good model for many real systems that appear in control applications, one of them being an industrial robot, as shown here, and we will later see why. So as a preliminary to this, we need to understand that the important preliminary information to have in here is that Newton's second law of motion also applies for rotational motion. So Newton's second law of motion for rotational motion, it's simply an analog to the linear motion, Newton's law of motion. In fact, in linear motion, we know that the sum of forces, or the net force, is equal to mass times acceleration. In rotational motion, we have the same or similar relationship, where we say the net torque, or the sum of torques acting on a certain mass, would be equal to the rotational inertia of the system times the angular acceleration. So the sum of torques is equal to moment of inertia multiplied by angular acceleration. That's what the rotational second law of motion says. So I is the rotational equivalent of mass in the linear sense. Now, when we're talking about torque, we are simply talking about the turning force about a certain fulcrum. So in this case, if you have a force, say F, as illustrated here, and then you have a link where the force is turning about the fulcrum, which is O. The turning force, when we talk about torque, we are talking about this force that acts perpendicular to this fulcrum. So in this case, the torque will simply be F times R sine of theta. So this will be the turning force. Now let's look at the pendulum model itself. So a pendulum model can be a good model for a robotic hand driven by a torque, which is being used, say for example, to pick material from bucket A to bucket B. Now, as the arm of the robot swings from one place to another, you can see that this has it's similar in behavior to the pendulum. So the pendulum can be used as a useful model for modeling such a robotic system, an industrial robot system. Now, in our model for a pendulum, we have a fulcrum here, or a pivot, whereby it's attached to a massless rod. We want to make it massless because it simplifies our analysis in order to demonstrate our point. Otherwise, we all know that if it is an iron bar or say metal, it will have a certain mass. I think a good assumption is to assume that the mass at the end, in this case, that is whatever the industrial robot is carrying, is significantly heavier than the arm of the robot itself. So we want to form a relationship as to how the input torque put on the pivot or around the pivot, it will relate to the angular displacement. Now, by Newton's second law of motion, we know that the sum of torques is equal to the moment of inertia times angular acceleration. Now, since we have made an assumption here, like I said, that the rod is massless in order to simplify our calculation for the moment of inertia. So, according to the Newton's second law of motion, now the sum of torques here, it will be the input torque. This would be the input torque that the motor that drives the robot will be putting in, and this torque will be negated by the torque which is generated by the mass itself, because at any point there is mass. This mass is heavier, so which means there is a component of force that drives this pendulum back to zero. So the sum of forces in this case would be a component of this weight of mass, which is mg, which goes this way, in fact perpendicular to the mass, and that force can be simply obtained by extending a right angle triangle here. You will see that force is simply mg, which is this that force is simply mg times sine of theta, if there is theta here. So if mg is here, and you consider this is like a right angle triangle, this component of force that's here is going to be mg sine of theta, which is the torque that will be turning around the pivot L, which is a distance L away. So the torque would then be mg times the length of the rod times sine theta. That force will be acting against the driving force of the motor, which will be the input torque, and that should then be equal to the moment of inertia times angular acceleration. Now, because we have assumed that the rod is massless, a quick calculation will show that if the rod is massless, the moment of inertia for this particular model is going to be the mass of the ball at the end times L squared. So therefore, this becomes the equation of motion for our robot, which picks material from bucket A to bucket B, because then you make it equivalent to the pendulum. Now, if we look at this model that we have just come up with, we see that the model as it stands, it relates our output which we are interested in, which is the angular acceleration theta. It has a non-linear relationship here because it's sine theta. So sine of theta, the sine function itself, it's a non-linear function. You can remember sine of function changes this way. So because sine function is non-linear, it means the model here is non-linear. Now, we can be able to linearize our model with respect to zero, assuming that the robot only operates by shifting its mass to and fro from bucket A to bucket B, only using a small displacement between the two. It's a small displacement between the two. So if that displacement is small, if delta theta is small, around the angle 0, then we can linearize a linear model is as good as a nonlinear one. So the nonlinear function we are talking about here is this minus mgl sine theta. Now, in order to linearize, as we remember, if you have a nonlinear function to linearize, there are two things that you do. The first thing that you need to do is to take the first derivative of that function and evaluate it at the point where you want to linearize. So the first derivative of g will simply be equal to the derivative of sine theta, which is going to be cosine theta. And then we take that derivative of sine theta we assign its value, or we evaluate it at theta is equal to 0. So this would be minus mgl cosine of theta, but cosine of 0 in this case it becomes 1. So this is simply equal to 1. Therefore, we find that our proportionality constant is it's negative mgl. Therefore, it therefore means that our linear model, when you have linearized with respect to theta, that function is going to be mgl times the new variable here, theta. So this then becomes the linear model of the pendulum. If we look at the pendulum module, we will now turn our attention to the fluid flow systems. So control problems arising from fluid flow. There are a lot of control problems arising from fluid flow. They could involve controlling of pressure, controlling of a level in a chamber, or controlling the fluid, the rate of flow of the fluid itself. So fluid flow control problems are prevalent in petrochemical plants, such as the one shown here, in thermal power stations which are producing electricity or heat. In water management, there could also be a lot of level control problems there. Now, as a preliminary to understanding the control and modeling of fluid flow, we will first look at Bernoulli's law, the conservation of mass, and then we'll move on to a level control example, just to demonstrate how these two laws can be applied to create a model for a fluid flow system. So talking about Bernoulli's laws, so Bernoulli's law describes the behavior of fluid under varying conditions of flow and height, and it comes from the observation which has been noticed that an incompressible fluid, which is generally what we'll just look at, a fluid which cannot be compressed, or at least cannot significantly be compressed like water, conserves energy. So the flow of such a fluid conserves energy. So what Bernoulli's law simply says is the energy by virtue of pressure difference plus the energy by virtue of movement, which is kinetic energy, plus the energy by virtue of the height above the ground, or the potential energy of a fluid, as it flows, it remains constant. So energy, it's a conservation of energy law. So if we have 2 points, say point number 1 and point number 2, in a pipe, whatever channel is, as the fluid flows, what Bernoulli's law simply says is that if we look at these 2 points, the pressure in atmospheres at point number 1 plus half rho times v squared, which is the velocity of which is the velocity of flow, or the speed of flow at point number 1, plus rho times acceleration due to gravity times the height of that point, which is a measure of the potential energy. That energy combined will be equal to the energy of that fluid, of the very same fluid, when it's at point number 2. That is, at point number 2, the pressure at point number 2 in atmospheres, sorry, in pascals or in atmospheres, plus the component of kinetic energy plus the component of potential energy. This sum will be equal to that sum. So this is what Bernoulli's law states. Now, when we look at conservation of mass, we say in a closed system, as the fluid flows, we should be noting that the mass is neither created nor destroyed. That is, if you have a channel here of fluid coming in, at point number 2 and leaving at point number 2. At point number 1, what we can say is the change in mass that we observe within this has to be equal to, within this chamber or channel, has to be equal to the mass coming in minus the mass going out, because mass cannot be created inside the fluid or in this process, and it cannot be destroyed. We defined here then that the mass flow rate, the flow of mass, which is delta M1 at this point, the outgoing mass, delta M1, will simply be equal to the density of the mass times the area times the speed at V2. Remember, mass is in kgs and time is in seconds. So what we are saying is mass over time will be equal to the density. Density is in kg meters cubed. Remember, density is equal to mass over volume times the area. Area is going to be in mass squared. That is the area of this, the cross-sectional area, times the velocity, the speed at which the fluid flows, which is going to be meters per second. So we say this has to be equal to that. So if we look at consistency of the units here, we can see that in fact the m's here will cancel out, and then we'll just have, on both cases, we're going to have the units kg per seconds in both cases, which means this equation, in effect, it's consistent. So this equation holds for, this equation would be the mass flow rate, the outgoing mass flow rate, and similarly we can draw an equation as well of the incoming mass flow rate at point number 2, where we are saying the change in mass with time is equal to the density, because the density of the fluid doesn't change. It's the same fluid that entering here that's also leaving here. The density is the same, times the cross-sectional area, which case here is slightly bigger, times the velocity, at which case here should be slightly slower because the cross-sectional area actually is bigger. So for an incompressible fluid with no gaps in between, what we are saying is that because no new mass is being created here, the mass coming in will be equal to the mass going out. This is the conservation of mass equation. So having looked at the two important equations here, which is the Bernoulli's law and the conservation of mass, let us look at how we can model one such a simple fluid flow system. So this is a gravity flow outflow tank. So what simply happens here is that we have a container with a cross section A1, and this container, we regulate the height of the fluid in the container by controlling the input mass flow rate Q1 using a control valve. And what happens is at the bottom the fluid escapes, so there is an open outlet, and this fluid escapes at the flow rate of Q2. So if we increase the input flow rate here, Q1, so that Q1 is much bigger than Q2, we can intuitively tell that the height of the fluid in the tank will go high. If on the other hand we decrease Q1 so that Q1 is much smaller than Q2, we can tell that eventually the fluid level will go down. So now if we wanted to put an electronic controller on Q1 so that we can get the desired level of height of the fluid Z, how do we then model the relationship between Q1 and Z? That's what we are trying to do. So in the process, obviously, we see that the output equation, it's Q2. We also need to understand how Q2 is related to the height Z, because we can tell that if the tank is a little bit full, the output flow rate should be much bigger than when the tank is almost empty, because there will be a lot more pressure. So before we proceed further, we can tell that the mass of the fluid in the tank will simply be equal to the density times the volume. The mass of the fluid in the tank will be the density times the volume. The volume in this case, for our case, the volume is going to be A1 times the height, which is Z. So we can tell that the mass of the fluid in the tank is simply equal to rho A1 times Z. Now, by conservation of mass, in this case, we can tell that the derivative of mass of the fluid in the tank with respect to time is going to be equal to the mass flow rate of the incoming fluid minus the mass flow rate of the outgoing fluid. Now we both know that we have previously discussed that the mass flow rate of a fluid is simply equal to the mass flow rate of the fluid is simply equal to the density times the cross-sectional area times the speed of flow velocity. So that's what the mass flow rate will be equal to. So we can tell that this flow rate and that flow rate in this case will be equivalent to that. Now the mass here, we said the mass is equal to density times area times the height. So if we are looking at the derivative of mass with time, the only term that can change between this is that the density of the fluid is the same, the cross-sectional area of the tank remains the same, but the mass changes because the level of the fluid in the tank changes. Therefore, delta M, the first derivative M with respect to time will simply be equal to rho times A1 times dz dt, the derivative of the height with respect to time. And that should be equal to Q1, which is our control input, minus Q2. But Q2, from the relationship here, which I established, Q2 should be equal to rho times A2, which is the outlet, the cross-sectional area of the small outlet, times the outflow, V2. But we have already established that V2 has to be related to the height of the fluid in the tank. So we need to explicitly, in this equation, because this becomes the equation of our differential equation, we need to explicitly state how Q2 is related to Z, because there's a relationship between this, because we have observed that if the tank is full, the rate at which the fluid goes out will be much higher than if the tank is empty. So somehow V2 is related to Z itself. So we need to break down the V2 before we get the final model or the differential equation which relates Z to the input flow rate Q1. Now we can apply here Bernoulli's law. Remember, Bernoulli's law looks at the fluid or the energies of the fluid at 2 points. In this case, we will look at the flow rate here at point number 1 and the flow rate here at point number 2. So what Bernoulli's law says is the pressure at 1 plus the energy due to pressure, the energy due to kinetic energy, the energy due to potential energy should be equal to the energy due to pressure at point number 2 and the energy due to kinetic energy at point number 2 and the energy due to potential energy at point number 2 as well. So if we take our height here, so this should be the 0 of the height, and we take our height Z, we will notice that in fact we will take Z1, which is the height here, should just simply be equal to Z, because Z2 is going to be 0, because this one, the outflow occurs here at the bottom of the fluid. So Z0 will be 0. And since this is the pressure difference is not so much for this open vessel, the pressure here will simply be the atmospheric pressure, and the other pressure here will also be the atmospheric pressure. It therefore means that when we have this equation, we can translate this equation here, P equals half of rho V1 squared and then rho G Z plus the pressure here, P2, but we said pressure at P2 is simply equal to the pressure at P1, which is equal to the atmospheric pressure, plus half rho V2 plus this element, which is rho times G times 0, which is simply 0. Now, because of that, we can omit this 0 element, and because the pressures are the same here, we can remove this. We can take this to the other side, and the pressures will cancel out. And so we are left with this equation. Now, once we are left with that equation, we can rearrange it so that we move this to the other side, and then we factor it out. So the equation that we are left with is this. It's half of rho times the square, the difference of the two squares, the velocity squares, is equal to rho times g z. But we will notice that, in fact, what happens here is that the flow velocity here at the top of the tank here, the flow velocity at the top of the tank compared to the flow velocity at the bottom of the tank, it's huge. So because this is big here, the speed of flow here is going to be very small. So V1 is going to be very small. But V2 here, because this is constricted, V2 is going to be big. This means, therefore, that the square of V2 is going to be much bigger than the square of V1. So much big that so big that when you have the square of V2 minus the square of V1, you effectively, this is insignificant. So this is basically the square of V2 minus the square of V1 would approximately be equal to the square of V2 itself, because V2 is much bigger. For this reason, we can rewrite this equation to simply show that one side remains half rho times the square of V2. We don't need that square of V1 because it's so small. Now this means therefore the rho GHZ is approximately equal to 0.5 rho V2 squared. Now we can rearrange this equation so that we are left with V2 on one side. So V2, which is the outflow speed here, at point number 2, is going to be equal to 2 times G of Z. So in fact, our hunch that the output velocity it's a function of Z, it's correct actually. So which means the height is it's proportional to the exit velocity. In fact, the higher the level, the more velocity output, the higher the speed of outflow, as intuitively as we had suspected. So taking this back to our modeling equation, so initially we have discovered that rho A1 delta Z dz dt is equal to Q1 minus rho A2 V2. But we have also discovered that V2 in itself is equal to the square root of 2 GZ. Substituting for V2 into the equation, we get this. We get that rho dz dt is going to be equal to Q1 minus rho times A2 dot V2. So what V2 is. So in fact, now rearranging these terms, that is dividing by rho A1, we will notice that our differential equation will therefore become dz dt equals to 1 over rho A1 times V1 minus A2 divided by A1 square root of G times the square root of Z. Clearly we can see therefore that the equation here, or this portion of the equation here, it means that this is a non-linear equation. It therefore means that the height is non-linear. So the model of the system that we are modeling here, the gravity tank, it's a non-linear system. And we can see, because we said initially that our outflow, which is Q2, which is equal to rho times A2 times V2, it implies that if you substitute for V2, then Q2 is going to be rho A2 times the square root of 2GZ. If you substitute that back into for V2. So we have a nonlinear model of the equation. So having developed that model, let's say now our objective is to linearize the output equation of our model with respect to the liquid level at some level Z0 is equal to A. So let's say we want to maintain a level here Z, which is equal to A meters in our tank for whatever reasons. Now we want to linearize this output equation with, at that point Z, at a point Z is equal to A. Now we notice that we can rewrite this equation here. We can rewrite it and separate the Z variable out of the rest of the variables which are parameters here, which is which is rho A2 cross-sectional area of the outlet times the square root of acceleration due to gravity. Now, if we want to linearize this, we know that we have to take the first derivative of Q with respect to Z. And because the rest of these other terms have nothing to do with Z, we'll also take the derivative of the square root of Z with respect to Z. So this would be the derivative of Z to the power half. And because of that, we know that this should be equal to half of Z to the power 1 over 2 minus 1, which is simply half Z to the power negative 1 over 2. So this should be equal to 1 over 2 root of Z. That should be the derivative, the new derivative that we have. So now, putting it back into that equation, this gives us rho times A2 divided by G divided by 2 times 1 over root of Z. But our linearization has to happen so that Z is equal to A, which means then our proportionality constant here is going to be as substituting the A for Z. So we are going to have the dz, the Q2 dz is going to be equal to, rho times A2 square root of G divided by 2A all over 2A. Now it therefore means that the linear part of the model would be equal to this proportionality constant which we have just derived here times Z. That should be the linear approximation of the model. So having looked at this lecture, you should be able then to have a basis of how to analyze fluid flow systems and a pendulum oscillator and how it's applied and how you can linearize nonlinear models or aspects of the nonlinearity in the models that you derive. Go to the tutorial for exercises, look at your study guide in order to read the relevant sections of the reference text, and then look at the text so that you can find some more problems which you can solve relating to fluid flow systems as well as the pendulum oscillator.